Hey guys, my name is Tensor. Welcome to the final video of our Go blockchain tutorial series. In this video we will be taking the network module that we built in the last video and interfacing it with our blockchain. Then we'll be able to run the actual blockchain in multiple different instances and see how each of the nodes communicate with one another. To make things a little bit cleaner, I took the blockchain iterator struct along with its methods and put it into its own file called chain_iter.go. I did this because we're going to be adding a lot to the blockchain file. Let's start by adding some utility functions that we're going to need for our network. So we need to be able to deserialize transactions from bytes into the transaction structure. So we'll create a deserialize transactions function. This follows the pattern of all of our other deserialize functions. We get the structure that we want to deserialize into, then we take the data, we read it in with our bytes reader, and we pass it to a gob decoder, and then we decode it into the transaction struct. Because we're going to have multiple different copies of our blockchain, we need to modify the block structure so that it will contain the height. And actually, while we're in here, let's also add a timestamp field to each of our blocks, so that each one is unique based on when it's created. Adding the height to our block struct will make it very easy for us to get the actual index of this block in the chain. So when we compare two chains together, if one of them is say length 2 and the other one is say length 4, we know that there are blocks 3 and 4 that we need to add to the other chain. And we can contain each of the blocks index in this height value here. Because we now have the timestamp and the height in each of our blocks, we need to modify the create block function. So for the timestamp, we can just call time now Unix, which will get the current Unix timestamp. And then for the height, we can just pass it into this function as an integer and then put it into the block. We also need to modify the Genesis block and add the height because we're calling the create block function. And the height, of course, of the Genesis block will be 0 because it will be the first block in our blockchain. Inside of our blockchain.go file, we have a bunch of constants, and we use this manifest file to determine whether or not the database exists for our blockchain. Because we're going to have multiple different blockchain databases, we need a different way of determining whether or not the database exists. We can go ahead and delete the db file and replace it with this db path constant. The db path constant will just look at the actual directory itself, which will be inside of our tmp folder, and it will be a folder called blocks underscore followed by the node ID. This will make it so that we can have multiple databases for each of our nodes and have them be represented in different folders. For the dbExist function, we want to pass in the path as a string, and we can still use this osstat command to find out whether or not the path plus the manifest file exists. And again, we'll return false if it doesn't exist, and we'll return true if it does exist. Speaking of our database, I'm going to go ahead and add two new utility functions for the Badger database. One of them is called retry, and then the other one is called Opendb. These two functions exist to make it so that if we do corrupt the data for a Badger database, we can retrieve that data. So first let's look at this retry function. The retry function gets executed inside of the Opendb function if there is a lock file inside of the database folder. The lock file is a file that exists when another process is accessing the database. If the process that's accessing the database is cut short without being able to garbage collect the data, then this lock file will be left in that folder. So we want to delete the lock file, and that's what we do inside of this retry function by using this os_remove command. And then we get the original options, which we're passing in here, these Badger options, and then we change part of the options to make it so that we truncate the actual database, and then we try to reopen the Badger database with this new option. Without going into too many details, this will allow us to recover our database if one of our processes exits prematurely. The Opendb function is pretty straightforward as well. We just call Badger open with the options. Then if we get an error, we want to check to see if the lock file exists. And then if the lock file exists, we call our retry function. Otherwise, we just print out that we couldn't unlock the database. And then if all of this works out and we don't get back an error, we just return the database from this function. Let's now come up to our continue blockchain function and modify it so that it will account for the different nodes that we have. So for each of these functions, we want to pass in a node ID, which will be a string, and then we can use that node ID to check to see if the database exists for that particular node by combining the DB path with the node ID. Then rather than opening our database with just badger open, we can call our OpenDB function so that we can account for a lock file in our database folder should our process exit prematurely. We also need to modify the init blockchain function. Before it just took in the address as a string, and now it takes in both the address and the node ID. Again, we create the path by passing in DB path and the node ID, and then we check to see if the database exists. Then of course we can just open our database with our OpenDB function and the path and the options, and then of course run the function like we were before. Below we have this add block function. We want to change the name of this function into MineBlock because we want to create another add block function to our blockchain structure. And along with changing the name of this method to MineBlock, we also need to account for the height inside of this method when we create our block. So we can create a new variable here called last height, which will be an integer. Down here we're opening up the database to read the last hash out of it. We can go ahead and use that last hash to get the last block, and then we can deserialize the last block and then get that last block's height and put it into the last height. Now down here where we're creating the new block, we can pass in the last height plus 1 to increment the last height. Now let's go ahead and create the add block method. This will take in a pointer to a block, and inside of it we can open up the database and update the database by adding a new block to it. We'll use our transaction get to check to see if the block is already in our blockchain. If we don't get back an error, then we just want to return from the update function because that means that the block is in the database. Otherwise, we want to take our block and serialize it and then set it inside of our database with the block hash being the key and the block data being the actual value. Then from there we need to get the last hash, so we'll call transaction get on the LH key. Then we'll get the value from this item. Then we can go ahead and call transaction get last hash, which will get the last block in our database. Then we want to get the value of this last block, and we can then deserialize it back into a block, and then we can check to see if the block height of the block that we just added to our blockchain is larger than the last block's height. And if it is, then we'll set the new last hash as the block hash, and then we can add it to our blockchain structure like this. Now, along with the add block method, we also need to create a few other methods on our blockchain. We need a method so that we can actually get a block based on the block hash from the blockchain, and this will return a tuple of block and error. We create the block variable, and then we open up our database using a read-only transaction. Inside of here, we can call transaction get on our block hash, and then if we have an error, then we want to return that the block was not found in the blockchain. Otherwise, we want to get the block data by calling item value, and then we want to deserialize the block data back into a block, which we can then return from this function. We do need to add a small little if statement to check to see if we get an error from here, and if we do get an error from here, then we just want to return the block variable, which will be empty, and then the error itself. Now we need a method that will allow us to get all of the block hashes from our blockchain. So we'll create a two-dimensional slice of bytes called blocks, and then we'll use our iterator to iterate through the chain. And again, the way this works is we open up a for loop, and then we call iter next, which gives us the next block. And then when we get to the end of our blockchain, we have a empty previous hash, which will have a length of 0, and then we can just break out of the for loop. All we're really doing is taking the block that we get out of the blockchain, grabbing its hash and then appending it to our block's structure. So all of our hashes will be appended onto one another, and this will allow us to quickly verify if the copies of our blockchain are the same. Finally, we need a method that will allow us to get the best height or the last height in our blockchain. So here we can create a block variable. Then we can open up our database with a read-only transaction. Inside of our database, we want to get our last hash, and then we want to get the block associated with that last hash. Then we can deserialize that block into the last block, and then we can return the last block's height. Along with having multiple copies of our database, we also want to have multiple copies of our wallet.data files. So let's go into our wallets.go file and modify this constant so that we can have multiple different wallets.data files. So again, like before, we just want to modify the string and add this %s so that we can append the node ID to the wallets file when it gets created. Now we can modify the save file method and the load file method by passing in the node ID as a string and then appending it to the wallet file constant using fmt sprintf. And now when we save the file, it will have the node ID at the end of it. Up here in load file, we also pass in the node ID, and we also use fmt sprint to concatenate the wallet file constant with the node ID. Then we can just check to see if it exists by passing in the wallet file. And then we can of course create a new file, which is using the wallet file's name. Now inside of the create wallets function, we just need to pass in the node ID as a string, and then we need to pass it into the load file function. The rest of what we're going to do in this tutorial will be happening inside of our command line interface module. Let's go ahead and import our network module into this file, and then we can create a new flag inside of our print usage function. The new flag will just be called start node, and it will have an optional string attached to it called miner, and we can input an address here to indicate that we want this node to be a miner node. We need to also specify a node ID environment variable so that this node will actually have a node ID attached to it. Also, we want to edit our send transaction command. Before we were just passing in the from, the to, and then the amount. We can also now pass in this mine flag, which will tell the node that we want to mine the transaction with that node. We can use this when we don't have any miners attached to our networks. So this will allow us to create multiple blocks in our chain before we have to connect a miner node. Now let's come down here and add the start node function to our command line interface. We'll just print out that we're starting the node, and then we'll pass in the node ID. So it'll be like node 3000, which will be the port, or node 4000, which will be the other port, and so on and so forth. Then we want to check to see whether or not we have our miner address being passed in. And if the miner address is being passed in, we want to call wallet validate address on the miner address, and then we can print out that we're mining on the address, and then that address will receive the awards. Otherwise, we'll just print out that we have the wrong miner address. And then afterwards, we can start our server with the node ID and the miner address inside of it. We also need to modify a lot of our commands. So the reindex UTXO needs to take in the node ID with a string, because we need to pass the node ID to our continue blockchain method here. We need to do the same thing for list addresses, because as you can see, create wallets needs to have the node ID inside of it. So again, we'll just pass in the node ID as a string, and then we'll pass it to create wallets. Again, we have the same thing going on for the create wallet command, where we need to pass in the node ID as a string, and then pass it to create wallets and the save file method. The print chain command is also going to need the node ID, because we're calling continue blockchain inside of this command. Down in create blockchain, we also need to pass in the node ID, because we're calling the init blockchain function, and this takes in the address and the node ID, so we can pass that string in here as well. Get balance also calls continue blockchain, so we need to pass in the node ID. And then of course the rest of it is exactly the same. Now the command that we need to change the most is this send command. We pass in the from and to strings, then we pass in the amount, which is an integer. We need to pass in the node ID, and then we need to pass in the mine now boolean. We'll create our blockchain by calling continue blockchain on our node ID. And then of course we pass it in the UTXO set, and we defer closing the database. Then we need to take the node ID and call create wallets on it so that it will open up the appropriate file. And then we need to get our wallet from the node ID using the from address. We can then create the new transaction by passing in the from address's wallet to the amount and then the UTXO set. And then we want to check to see if mine now is true or false. If it's true, we need to create a Coinbase transaction for the from address. Then we need to create an array of transactions with our Coinbase transaction inside of it, and then the transaction we created here inside of it. Then we'll mine the block using mine block, and then we'll update our UTXO set with the block. If we do not want to mine it, then we want to call network send transaction, and we'll call to our known nodes index 0, which will be our localhost 3000, and then we'll pass in the transaction, and then we'll print out that we sent the transaction. Down inside of our run function, we need to be able to parse the node ID environment variable, and we can do this by using os.getEnvironment and then passing in the name of the variable that we want to parse. And then if we do not get a node ID, then we want to exit our application, and we want to say that the node ID environment variable has not been set. Now we can go ahead and add our new flag, which is the start node command. And then we also want to add the new substrings. One of them is the boolean for the mine on send, and then the other one is a string on the start node command. As with all of our other commands, we can add a new case to our switch statement for the start node command. And then down where we're calling all of our CLI functions, we need to modify them so that we pass in the node ID. So as you can see here, with getBalance, we pass in the node ID. We do the same with create blockchain, with print chain, with create wallet, list addresses, and reindex UTXO. For send, we also want to pass in send mined, which will be a pointer. And then for the start node command, we just want to check to see if the node ID exists. And then we want to pass in the node ID and then the start node miner flag. Because the start node miner flag and the send mine flags are optional, we don't want to put any kind of if statements here to check to see if they exist. Let's go ahead and set up our command lines. So I've got 3 different command lines open here. I'm going to set up the node ID environment variables first. And for Windows, it's just the set command. For Linux, you can use export. And so this one will be port 3000, this one will be port 4000, and this one will be port 5000. Now let's go ahead and create wallets for each of these. And then for node 3000, I'm going to create a blockchain. If we look inside of our TMP folder, you can see we have this blocks 3000 folder, and then we have all of our wallets files. So I'm going to go ahead and take the blocks 3000 folder and copy it to blocks 4000 as well as blocks 5000. And then I'll also make a folder called blocks gen, which will hold the original Genesis block inside of it. So now each of these nodes has the same blockchain. To differentiate the blockchains, I'm going to add a block to this blockchain here, and I'm going to make the local blockchain mine it by passing in the mine flag. So I'm sending from this account to, I believe it's this account, 10 tokens, and then I'm going to mine the block with this blockchain. And of course this works as you would expect. It just mines out the block and then it says success. And now we can go ahead and start the node here and then start the node here. And you can see this is actually copying the block and then writing it into its own blockchain. Over here on this big screen, I'm going to open up this node as a miner. So start node with the miner flag and then the address for this wallet. And you can see here that it goes ahead and it copies the blocks from this node and it then writes them to its own chain. Now with this blockchain, I'm going to exit out of the start node command so that we can start to make transactions. So now let's send a transaction. So I'm going to send a transaction from this address to this address, and I'm just going to send one token. You can see here after it sends the transaction, it says sent TX, success. And then for the two nodes, it shows us that there's one transaction in the inventory. If I go ahead and create another transaction, you can see our miner goes ahead and mines a new block, and then the new block gets added to the central node. And we can of course run our start node command for this node to download that new block into this blockchain. On each of our nodes, we can go ahead and print the chain, and you can see we've got a pretty long chain now. We can also go ahead and get the balance of each of our wallets. You can see here this is the balance of the miner wallet. And because we have blockchains on each of our machines, we can run the get balance command on any of the wallets in any of the nodes, and it should work. Now the main downsides to this implementation is that this node here is the centralized node, which means that this is not technically decentralized. Also, when we're running a send command, it needs to be from a wallet that exists inside of the node, because when we run the send command, it actually goes and looks for the wallet based on the wallet's file. And the final major difference between this and a major blockchain is that when it goes and downloads a new block, it actually goes and downloads the entire blockchain. Alright guys, well I hope you enjoyed this tutorial. If you did, feel free to like and subscribe. If you have any questions or comments, feel free to leave them in the box below. And if you disliked this video, then by all means downvote it as much as you like. Have a good night.